Okay, so I will start with question number one. As we said before, we have here the contingency table. Okay, the contingency table is for listing the values of two variables. Okay, we have cells. Each cell will have some counts. If it doesn't have counts, if the cell doesn't have counts, so this means if it has a probability or a proportion, so this refers to the probability of intersection between the row and the column. Okay, so for example, this 0.44, okay, so this 0.44, it is just the probability of the intersection between yes for needing glasses, so needs glasses, and yes for using the glasses for reading. Okay, so uses glasses for reading. Okay, so this is what we mean by the probability of any, or by the value in any cell. Okay, so this probability is obtained by dividing the count of this cell by the total of the sample. Okay, now the question is saying if a single adult is selected from a large group, find the probabilities of the events defined below. The adult needs glasses. Needs glasses, where do we find needs glasses? So needs, yes, needs. So this means I'm going to add the probabilities in this row for needing glasses. So it's going to be 0.44 plus 0.14, which is going to be 0.85. Needs glasses but doesn't use them. So needs glasses, so I'm in this row but doesn't use them. Okay, for reading, it's 0.14. Uses glasses, whether uses glasses, so I'm using glasses whether needed or not needed, so it's going to be 0.44 plus 0.02. So this is for question one. That's what you need to learn from this question. The conditional the joint probability, or the probability of the intersection, this, and the probability that you get by summing the row, or finding the total of any row and finding the total of any column. By finding the total of any row or any column, so this means you find the marginal probability, okay, not the probability of intersection. Next question, how many different 7-digit telephone numbers can be formed if the first digit cannot be 0? So we're going to choose from numbers, we're going to choose a number from 0 to 9, okay? And we have 7 places to fill. The first place cannot be 0. So this means instead of having 10 choices, I have 9 choices. But for the rest of these places, every place I can choose from 10 numbers, okay? So the first number, because it cannot be 0, so I will have 9 choices. I can choose by 9 different ways, or this place can be filled by 9 different ways. For the rest of the places, we're going to fill them by 10 different values, or we have the options, or we have 10 choices for each place. So this means by how many different 7-digit telephone numbers can be formed, it's going to be 9 times 10 power 6. I'm going to choose 7-digit number, or I'm going to form a 7-digit number. How many 7-digit numbers can be formed? Okay, just the first place has 1 choice less. So this is for the second question. Third question, I have 10 teams are playing in a basketball tournament. In the first round, I have the teams are randomly assigned to games 1, 2, 3, 4, and 5. By how many ways can the teams be assigned to the games? So you need to think about how you're going to conduct this experiment or this process. So I'm going to split this process into 5 different stages. The first stage is the first game. Second stage is the second game. Third, fourth, and fifth. In the first stage, I need to choose 2 teams out of 5. The order of the teams is not important and repetition is not allowed. Why? Because no team can play with itself. So this means for the first game, I can choose 2 out of 10. While for the second game now, because I have chosen 2 already, I'm not going to include them this time, so I'm going to choose 2 out of 8. Then for the third game, I have now 4 teams less, so I'm going to choose 2 out of 6. For the fourth game, I will have now 6 teams less, so it's going to be 4. I'm going to choose 2 teams out of 4. And then for the last game, I only have 2 left, so I have no choices. It's only one choice. I have no other choices. It's only one. So for every stage now, I determine the number of ways to conduct every stage. So at the end, the number of ways to conduct the whole stages or the whole process is going to be the product of these stages. So this is going to be the answer for this question. Question 4. I have a student who prepares for an exam by studying a list of 10 problems. She can solve 6 of them. For the exam, the instructor selects 5 problems at random from the 10 on the list given to the students. What is the probability that the student can solve all the 5 problems on the exam? The student can solve the whole exam if the instructor chooses the 5 questions from the 6 questions that the student knows, which means by how many ways can we select 5 questions out of 6? Order is not important, repetition is not allowed, so it's going to be 6C5. But the process or the experiment that the instructor is going to conduct, the experiment, so the whole sample space, the experiment that the instructor is going to conduct, he can conduct it by choosing 5 questions out of 10. So the probability that the student is going to solve the questions or the exam correctly is going to be C6C5 divided by 10C5. How do we get, or why did we use this ratio? Because we know that in order to obtain the probability, we need the number of elements in A. So the 6C5 is the number of elements in A, the number of ways that the student can solve the whole exam, divided by the number of elements in S. What is S? S is forming the whole exam. So by how many ways can we form this exam? It is 10C5. Okay, so this is for question 4. For question 5, we solved it today, but I'm going just to give you a brief on this question. So if we know that probability, if we know that A and B are independent, so this means we know that the probability of intersection is going to be probability of A times probability of B. What we would like to show is that if A and B are independent, so A complement and B complement are also independent. Okay, so probability of A complement intersect B complement is going to be probability of A complement times probability of B complement. This is what we would like to show. Okay, so now I'm going to start with the left hand side. This is how we prove anything, so left hand side, probability of A intersect B complement, it's going to be using De Morgan's laws, it's going to be A union B complement. So it's 1 minus probability of A union B. Then I know that probability of A union B is given by probability of A plus probability of B minus probability of A intersect B, which is A probability of A times probability of B because of the independence. So it's 1 minus, okay. So it's 1 minus probability of A minus probability of B plus probability of A times probability of B. So it's 1 minus probability of A, and by some simple algebra, you can just take probability of B as a common factor, and what's left is going to be 1 minus probability of A. Now you have here 1 minus probability of A, 1 minus probability of A. Take them as, or take it as a common factor, so you will have 1 minus probability of B left. So this is going to be probability of A complement times probability of B complement. So now we showed that the left hand side is equal to the right hand side. So A bar and B bar are independent. Okay. Question 6. We were given the probability of A, probability of B, and the probability of the union. The question is asking for probability of A intersect B using the additive rule. So you have probability of A, probability of intersection is probability of A plus probability of B minus probability of A union B. So this is going to be 0.2 plus 0.3 minus 0.4, so it's 0.1. B, part B, it's probability of A bar intersect B bar. This is going to be probability of A union B complement, so it's 1 minus probability of A union B. So it's 1 minus 0.4, and this 0.4 is given in the question. C, probability of A bar union B bar, it's equal to probability of A intersect B complement. So it is 1 minus probability of A intersect B. So it's 1 minus 0.1, the value that we have obtained in the first part. So it's 0.9. Now part D, probability of A bar given B. So as I said before, when you have a conditional probability, this means you have reduced your sample space. So you don't look at B. So you just consider this part only. So it's going to be 1 minus probability of A given B. So 1 minus probability of A given B, this is a conditional probability. You get it using probability of A intersect B divided by probability of B. Probability of A intersect B is 0.1 and probability of B is 0.3. So this means you have 1 minus 1 over 3. So it is 2 over 3, and this is the answer for this question. Okay, question 7. Again, it's about the condition, about the contingency table. Here we're not given the probabilities. We have the counts. Okay, we have 2 variables, sex and outcomes. We have male, female for the gender, and we have pass or fail for the exam outcome. Okay. Now the question is asking, are the events A and M independent? Do you think that A, the passing, is independent from male? So this means you have to check the independence using any of the 3 rules that we have mentioned in class. So I'm going to choose one of the rules, which is probability of A given male, and then I'm going to compare it with probability of A, probability of passing. If they are equal, then the 2 events are independent. So probability of A given M, so this means I'm going to reduce my sample space to just males. I know that I have 100 in total, but I have 40 males. So this means when I'm going to calculate my probabilities, I'm going to calculate or to divide by the number of people in my reduced sample space, which is 40. Now, how many passes in or within males, we have 24. So the probability is going to be 24 over 40, which is 0.6. What about probability of A in general, in total? So I'm not talking about probability of intersection nor any conditional probability. So it's going to be 60 divided 100. 60 divided 100. So it's going to be 0.6. Both are equal, which implies that A and M are independent. Okay? Also, the question is asking for A and F. So we're going to do the same. Probability of A given F, so it's going to be 36, okay, over 60, which is another 0.6. Probability of passes, we have it here, it's 0.6. Both are equal. Then A and F are independent. Okay, so this is for question 7. Okay. A diagnostic test for a disease is such that it correctly detects the disease in 90% of the individuals who actually have the disease. So this means this 0.9, it's a conditional probability. So I have correctly detect the disease. So let's say that it's positive, given that I have the disease. This is equal to 0.9. I'm going to change the wording of this question, so we'll have a different question. Okay, but I'm going to solve the question now using this wording, and I will show you the difference between the two types of questions. So positive given disease, it's 0.9. Also, if a person doesn't have the disease, the test will report that he or she doesn't have it with a probability of 0.9. So this means another 0.9, but this will give me a negative result if I don't have the disease. Okay, so it's another 0.9. Only 1%, so I have the probability of the disease itself, it's 0.01. This is the 1% that we have here. If a person is chosen at random from the population and the diagnostic test indicates that she has the disease, so I know now that she has the disease, so the result is positive, okay? And because he said that she has the disease, so the result is positive, the result of the test is positive. What's the probability that she has the disease? Okay, I'm going to solve it again using different wordings or different understanding of the question, and I will show you the difference. Okay, so let me draw the tree diagram. So here I have disease and no disease. Disease, only 0.01, and the rest is going to be 0.99. When you draw the tree diagram, what you put here at the very beginning is going to be the marginal probability, while what you put next is going to be a conditional probability on what you have at the beginning. So 0.01 here, and then I have here, this is 0.9. It is positive, given that I have the disease, and if it's negative, the result is negative. Given that I have the disease, it's 0.1. In here, it's going to be positive, negative again, negative with 0.9 and positive with 0.1. Okay? So now the question is asking for this probability. Okay? This probability. So it's a conditional probability. I'm not going to mention the name of the rule, which is Bayes rule, but you know why it is a Bayes rule question? Because we know that we should have the order of these events, or the order of the occurrence of these events is you have the disease and then you see the result of your test, not you have the result of your test and you don't know whether you have the disease or not. So it's not in the right order, so therefore we're going to talk about the Bayes rule. However, it's again another conditional probability that we need to calculate. So the probability of disease given positive, so it's going to be disease and positive divided by probability of positive. Okay, probability of disease and positive, so it's going to be the multiplication or the product of this part of the tree, it's 0.01 times 0.9. So you have the disease and the result is positive. So it's 0.01 times 0.9. Now, what's the probability of getting a positive result? So you could get a positive result if you have the disease, or you can get the positive result if you don't have the disease. So you have two possible options to get a positive result. So it's going to be 0.9 times 0.01 or 0.99 times 0.1. Okay? The other way of reading the question, which is not correct, but we could have it in the exam or we could have it in any question, okay? Maybe what I'm going to say here, that the test detects correctly. I don't know whether the detection is positive or negative. What I know is a correct result, okay? So a correct result, it's going to be here. Okay, a correct result is going to be here, okay? In this part, it's a correct result because I have the disease and it's positive. And the correct result is going to be here. Okay, so now I know, okay, so, and the diagnostic test indicates that she has the disease. No, I'm going to replace this, that the diagnostic test gives or gave a correct result. But we don't know whether this correct result is positive or negative. I mean, whether she has the disease or she doesn't have the disease. So in this case, I'm going to write what's the probability of having the disease given that the test is correct. So this means I need to find disease, probability of disease and correct, divided by probability of being correct. Okay, disease and correct, so this means it's 0.9 times 0.01. Probability of correct in general, you have the disease and the result was correct, or you don't have the disease and the result was correct too. So it's 0.01 times 0.9, okay, plus 0.99 times 0.9, okay? This is just a different way or another question. I solved it with one of the classes using that the test gives a correct result. So this was the question in one of the classes. So I can have the two questions, or I can have the questions written in the two different forms, and according to what's given in the question, you should choose which way you're going to solve this question. Okay, so this is the end of this exercise. Okay, just read the solutions, and if you have any question, just text me on WhatsApp. Thank you.